Okay, thanks. So yesterday we started our course with some basic features of Majorana fermions, Majorana bound states. Let me maybe spend 5 minutes again to remind you of what I told you yesterday, because repeating is learning essentially. And then we go on. We were basically in the middle of part 2, and the main aim is today to discuss the realization of this Kitaev chain in experiments, or how one can move towards experiments using this realization. So we have seen that instead of usual Dirac fermions, we have these zero-mode Majorana fermions that obey this Clifford algebra. So these are operators that anti-commute for different fermions, but there's no way you can count a state of a single Majorana bound state. So gamma dagger gamma is just a number, you cannot count the state. But what you can do is you can count pairs of Majorana fermions. So yesterday I asked the question, is there a Majorana C or not? And maybe you have an answer to that. So we know in principle we could pair them to build fermions, and then we might expect a Fermi C. And that's also true if the Majoranas come close together. But if they're all very far from each other, you have a degenerate manifold of zero modes. And what I told you yesterday is that in this degenerate manifold of zero modes, you can now move by braiding. And that's a state that is very different from what you have in a Fermi C. But it's a non-abelian state of matter, so there is no Majorana C once these Majoranas are very far from each other. And that's why you are not allowed to go there during my lecture. So we have seen counting Majorana fermions is possible by using auxiliary fermions that combine two Majoranas. This you can always do, but it's a non-trivial statement if gamma 1 and gamma 2 have spatially different support. So if they live at different regions of space. Yeah, you can of course always decompose a fermion like this, but it's only non-trivial if you really have different support. And then the parity of this pair of Majorana fermions is linked to the occupation of this zero-mode fermion operator. And as I said, we have this U1 degree of freedom here. We can also choose it with a phase phi in this definition. Then we have seen in S-wave we cannot really build such particles because the spin spoils the picture. We should have spinless particles. The way to do is, for instance, in P-wave superconductors, to get rid of the spin, you can either use vortices in a two-dimensional P-wave superconductor, or this route via one dimension, the Kitaev chain, which we then spend a lot of time on the Kitaev chain. It's this model here, hopping of spinless fermions on a chain of n sides. First we studied the open boundary case. You have a hopping, a pairing term that is proximity induced, and a chemical potential. And if you put mu to 0 and delta equal to t, there's a simple solution, simply by representing each fermion in terms of two Majorana fermions like this. You see that then the diagonalized model simply pairs these shifted Majorana fermions. And so all these particles in the bulk live at finite energy. So they're essentially at the gap or above the gap. But you have these zero modes sitting at the boundaries, gamma left and gamma right. They commute with the Hamiltonian. They are true zero modes, eigenstates. And these are these fractionalized zero modes that we have in this system. So we can build new fermions for the bulk. So all these, they sit at finite energy here, and that means in the ground state they're not occupied. But you have this F fermion mode, it's a true zero mode describing these two boundary Majoranas. And that means that we have a degenerate ground state. This is a topological degeneracy, namely you have either even parity or odd parity ground state, and you can move between them by action of this Majorana operator. Yeah, so the different fermion parity, and as we saw it, they cannot be connected by local operators. So that also means that we have a topological protection. Only non-local operators can really change between these two parity ground states, and that's one of the ingredients for schemes that are called topological quantum computation. And we have seen the fractional Josephson effect as one hallmark, and in fact also saw that we have indeed these non-abelian anyons. So that was part of this first part, and in the second part I then went into the bulk description of the Kitaev chain. So by taking periodic boundary conditions, put this Kitaev chain on a ring, we saw that there is a bulk boundary correspondence. So in the phase where you have a non-trivial topology, so a topological index equal to -1, we have a non-trivial winding. And once you cut such a chain, so once you introduce surfaces, these will have these Majorana end states. That's the general bulk boundary correspondence. So a topological insulator or topological superconductor has a gap in the bulk, but it has a non-trivial winding property in the map from Brillouin zone to the Hilbert space. And this reflects in boundary states once you bring in an edge or a boundary to the system. So once you cut the chain. Yeah. So the main part today will go into region 2. Kitaev chain can be realized in the lab. Just to remind you, we went then in periodic boundary conditions. We introduced K-space operators because with periodic boundary conditions you have translational invariance, so you can use conserved momentum K. And in this Nambu notation where we combine a particle and a whole operator, the relevant Hamiltonian in particle whole space is the Bogolyubov-Duchenne BDG Hamiltonian. So here you have the kinetic energy of the particles, kinetic energy of the holes is just the negative of it, and the pairing terms mixing particles together, yeah? Or holes together. In that, here we have the p-wave pairing potential in Fourier transformed language, so it's asymmetric in K, antisymmetric. Kinetic energy is just symmetric. And now one simply has to diagonalize this 2x2 matrix that amounts to a Bogolyubov transformation. So the diagonalized particles will have a mixture of particles and holes, and the eigenenergy is simply given here. And we then identify the phase diagram by looking for the zeros of this energy. Yeah? That's the general argument. As long as you're in a gapped phase, you can change parameters like chemical potential or hopping. You will not change the character of the phase. It's either topologically trivial or not. But once you go through a gap closing, you can then reopen the gap on the other side, and then you might be in a different phase. So to go from one gapped phase to a different gapped phase in general, you have to close the gap somewhere. So we have to look where this energy can vanish, and we found there are two possibilities. Either it can vanish in the center of the Brillouin zone if mu is equal to -t, or it can vanish at the boundary of the Brillouin zone when mu is equal to t. Yeah? And that means we have basically a topologically trivial phase when the absolute value of mu is bigger than t, and this topologically non-trivial regime when mu is small, absolute value less than t. And this is the regime where you get Majorana states when you cut the chain. We could then see this directly from the map, from the Brillouin zone, K, to this unit sphere that corresponds to the space of the Hamiltonians. So the Hamiltonian, this BDG Hamiltonian, looks exactly like the Hamiltonian of a spin. Spin being now defined in this particle hole Nambu space. And B of K is now composed of the pairing amplitudes and of this kinetic energy. So the Z component is the kinetic energy, it's even, and the XY components come from the pairing amplitudes. Yeah? So we have seen that this map is really restricted at the 2 points, k equals 0 and k equal to pi. These are the relevant boundaries that we have to look at in this map, and they have to point along the z direction, either up or down. So we start, say, at the North Pole, and the question is now, will we end at the South Pole, or will we end again at the North Pole? If we end again at the North Pole, this is the topologically trivial case, because we will not have to explore the whole sphere, this whole unit sphere of Hamiltonians. But if nu is equal to -1, we really are forced to do a winding. Basically, we have to go from North to South Pole and thereby explore the whole sphere. And that's a typical winding number. You have to go from here to here. How you go doesn't matter, but you have to traverse this region. Yeah? And so there is this C2 invariant, which is just the product of these two numbers. And you can now see that indeed in this region, mu between -t and +t, the yellow region here, is topological. And you have this non-trivial winding property in the bulk. The bulk ground state is still non-degenerate. It's a unique ground state. But once you cut it, you will have these boundary states. There is no Chern number in this case. So Chern number comes in quantum Hall physics, for instance, if you have a Chern-Simons theory for that. So it's similar in spirit as Chern's number, so it's an invariant, but mathematically this is not the same. So we then went on to construct the ground state. We saw that all the finite K modes, at least when we stick with the chemical potential close to the lower transition -t, the ground state will have finite Ks that are in the even parity sector, so you have a combination of Cooper pairs and unfilled states, so that will be an even parity part. And now the question is, what happens with this K equals 0 mode? We saw that in the topological case, this energy is below 0, so you will have an odd parity ground state because you will occupy that state. Yeah, so in this, with periodic boundary conditions, we had this odd parity ground state, and there's a gap to the even parity state. If you have antiperiodic boundary conditions, it's the other way around, because with antiperiodic boundary conditions, there is no K equals 0 state. So that means in that case, you would have an even parity ground state, and there's a strong sensitivity on which type of boundary condition you impose. It's typical for a topological phase, and nothing like this happens in the trivial phase. And indeed, we saw that if we put the whole system on a ring and change the boundary condition smoothly from antiperiodic to periodic, we start like this. So let's say we start with the periodic boundary condition. The lowest state is odd parity. There's a gap to the even parity. At the end of the journey, at the antiperiodic, it's the other way around. The even parity is down, the odd parity is up. And as you go in between, there must be a crossing. And here the crossing is precisely at the open boundary condition, and that's the state where you have a degeneracy between two ground states, namely this even and odd parity ground state, that are distinguished by the occupation of these Majoranas. So now that's where we ended yesterday. So now I want to show you that from this BDG Hamiltonian, we can also get the Majorana fermion directly by using a continuum description and assuming a spatially varying chemical potential. Things like this have been done for polyacetylene, for instance, where you have similar 0 modes, but there these are fermionic 0 modes. Here we have basically, because it's a superconductor, we have halved the degrees of freedom, so we have Majorana 0 modes. So let's see what we get from the BDG Hamiltonian. Let me go back. Here, this is our BDG Hamiltonian, and now we want to see a long wavelength, small k expansion of this Hamiltonian, and it will be sufficient to go just to linear order in k. It's a controlled approximation to drop already k² terms. So if we stay in linear order, psi k will just be replaced by -t minus mu, and the delta k will be replaced by linearizing the sign. Okay? So with this, we are at this Hamiltonian. Yeah? So that's the long wavelength approximation of the BDG Hamiltonian. And now to construct the Majorana state, we will assume that the chemical potential is not a constant, but a weakly varying function of x. I will construct it such that at x equal to 0, it is exactly at the critical point, which is minus t. And alpha is some slope of this chemical potential variation. It's positive, a small positive number. So for x negative, we are with mu below minus t, so it's trivial. For x positive, mu is above minus t, so we are in the non-trivial regime. And in between, there should be a Majorana state. Okay, so that's the idea. So if we insert this ansatz into the Hamiltonian, we see this is just minus alpha x. Here you have plus alpha x. And here k corresponds to the momentum operator. It's minus I dx. Yeah, that's the canonical quantization rule. So this Hamiltonian, the BDG Hamiltonian, looks like this. The 2x2 matrix in Nambu space, so in particle whole space. Now, there is a nice trick which I want to tell you. To obtain the spectrum of such a Hamiltonian, one simply squares it. So let's first write this Hamiltonian in terms of Pauli matrices. Tau z is 1 minus 1, so we have here minus alpha x times tau z. That covers these two. And these two really come from the tau y Pauli matrix, with P the momentum operator and a prefactor 2 delta. Okay? So now let's square this beast. Tau z square is just 1, tau y square is 1, and they both anti-commute. So you might first think the cross product will just cancel out because they anti-commute, but of course you have x dot p and p dot x. Here you have to be careful, so if you work this out, the squares give you alpha square x square, the other square is this, and now you get 2 alpha delta. If you look at tau z times tau y, that's minus I tau x, and then you have x dot p, that's the first term, so you have x dot p times minus I tau x, and now for the other term, you have first tau y times tau z. When you square, you have to have both orders, so you get a minus sign, and then p dot x. So that's why you have a minus sign here and p dot x. And because x and p don't commute, there is a contribution. Yeah? And in fact, x and p have the commutator I. I'm putting h bar to 1. So you have I times minus I is just 1. So you have tau x sitting here. So that's the Hamiltonian squared. And now you see that tau x is actually conserved quantity. So you can choose your Nambu basis as you want, as eigenstates of this tau x matrix. So this will just be plus or minus 1 in this choice. So h square will be alpha square x square plus the momentum operator square plus or minus 2 alpha delta. So, and then this is just a constant shift. We have p square with some mass. 1 over 2m is identified with 4 delta square. And we have an x square term. So this looks like a one-dimensional harmonic oscillator. And the frequency then follows by setting 1/2 m omega square equal to this prefactor alpha square. And now for this case, we can read off the frequency. You just multiply this by this. So omega squared fourth will be this times this, and you can read off what is the frequency of this oscillator. And we of course know the eigenenergies of the harmonic oscillator, h bar omega times n plus 1/2. And now this shift here is exactly half the frequency, and we have a plus or minus here. So what you get for the squared eigenenergies, E square, they are characterized by an integer index n, 0, 1, 2, and so on, and a plus minus sign. So we have h bar omega n plus 1/2 plus or minus 1/2. And now we are looking for a zero energy solution. So we put n equal to 0, the ground state of the oscillator, and pick the minus solution. So the E square 0 minus is clearly 0. That will be our Majorana solution. So we have n equals 0, ground state of the harmonic oscillator. That means the wave functions, so we are in NumBoo space, have a particle and a whole component. They must go in a Gaussian fashion. So we will have a e to the minus x squared over twice the length scale of the harmonic oscillator squared. So if you plug in our conventions for m and omega from these substitutions, you simply get this here. Alpha, I remind you, is the slope of this chemical potential as we go through the transition. So we see this is a mode that is localized around x equal to 0 on a length scale set by this oscillator, and that basically will tell you the steeper you make this transition. So as if this mu of x is very steep, then also the Majorana state will shrink. If it's a very small, smooth transition, of course it will be bigger in size. Now we still have a structure in this particle-hole space. Namely, we can see that from particle-hole symmetry, which is always fulfilled by these BDG Hamiltonians, this BDG Hamiltonian anti-commutes with tau x. So this you see directly here. The BDG Hamiltonian involves tau z and tau y. These both anti-commute with tau x. So the Hamiltonian must anti-commute with tau x. This in turn implies that if I have a solution for that spinor at energy E, I can construct a solution at minus E, because this is basically a minus when you write out this anticommutator, just by multiplying this solution with tau x. That's particle-hole symmetry. You get a solution at minus E simply from the one at E by multiplying the solution with tau x. And that also means if we have a solution at energy 0, the solution must be directly an eigenstate of tau x. Yeah? So we can infer from that u is equal to v. And in fact, in the continuum limit, writing the Cj's as field operators psi of x, you have the explicit construction of your Majorana bound state operator here. The upper component belongs to the particle and the lower component to the antiparticle annihilation operator, which is just the particle creation operator. Yeah? And that's evidently self-adjoint. And you see the wave function here is really localized around 0 in this construction in a Gaussian sense. I need high momentum to... Of course, you can include the k-square term, for instance, in this derivation. It will modify some quantitative aspects, but it will not modify the conclusion that there's a zero energy solution. Yeah? So I would say of course it's a correct point that we should, in principle, include this k-square term, because these type of Dirac problems with just the linear term, that tend to be tricky. But believe me, you can add the k-square term. It will change some of the analytical things, but there is still a 0 mode. Yeah. So much about the Kitaev chain model. So far, that's still a toy model, and the question is, how could I find such a model in nature? And people started seriously thinking about this about 5 or 7 years ago. One of the first ideas was to use spinless fermions, because we have to get rid of spin somehow, as I told you. To use a half metal, meaning that's a strong ferromagnet. Half metals are metals that have only one spin direction, or a large Zeeman splitting. But both of these ideas are difficult, because then the proximity effect from the S-wave superconductor basically doesn't work. So the idea that seems to work is to admix effective S and P wave pairing in one-dimensional nanowires by the interplay of 3 essential ingredients. Ingredient number 1 is we use a spin-orbit coupling, a strong Rashba-type spin-orbit coupling in indium arsenide or indium antimonide nanowires. So we will see this causes what is called a helical state. A helical state is a state where the momentum is closely linked to the spin direction. For instance, a right mover will have spin up, and then the left mover will have spin down. So in essence, you got rid of the spin because you know precisely what the spin is if you know whether it's right or left moving. This is achieved by the conspiracy of spin-orbit coupling and a magnetic Zeeman field, as I will show you in detail. Magnetic Zeeman field, you might object, a magnetic field is not so nice because it kills superconductivity. Fortunately, in these materials, one has very large Landé factors, order 40 or so. So you can have a large Zeeman splitting with a moderate or very small physical magnetic field that doesn't really kill the superconductivity, but already has a sizable Zeeman splitting in the material. Turns out that the orientation of this Zeeman field is not crucial. You should only avoid being precisely along the spin-orbit axis. Yeah? And then the third ingredient is that one brings a conventional S-wave superconductor close to this nanowire to have a proximity effect. Yeah? So to proximity induce superconductivity in this nanowire. Good choices seem to be niobium or niobium titanates. These materials make good contacts with these materials and thereby have a good proximity effect. So let me first go through these ideas pictorially, showing you the typical dispersion relations, and then later we will go through the algebra so you really see how this all works. So the starting point is we start with a Rashba quantum wire. Say that's typically a good model for indium arsenide or indium antimonide. So you have this wire with strong spin-orbit coupling sitting, for instance, on top of a substrate that is superconducting. In the recent experiments, typically the superconductors directly evaporated on the nanowire instead. Yeah? But let's, for the sake of concreteness, first forget about the superconductor and just look at a semiconductor. So you have a p square over 2m dispersion. It's just one channel for now. Then we add a spin-orbit coupling. What is spin-orbit coupling? It's essentially a relativistic correction, but you can also think about it as being caused by an electric field that is that comes from an interface. Yeah? For instance, there could be an electric field in this direction because you have the wire on some other material. Now, an electric field will act on a moving electron, so an electron that has some momentum p. In its own rest system, it will act like a magnetic field. Yeah? From a Lorentz transformation, you basically get that. And that will look like a vector product of E and P. There's some proportionality constant. Of course, this alpha is different from the alpha I just used for mu of x. So this is this sort of magnetic field in the rest system, which couples now to the vector of spin Pauli matrices. Yeah? That's just the Zeeman splitting as you know it. That's a way to think about spin-orbit coupling. So one sees this type of spin-orbit coupling can also be tuned by gate voltages affecting this electric field. And it is proportional to P, proportional to the momentum of the electrons. In this geometry, this would couple to the y direction of the electron. And the B we can take, for instance, in the z direction. Yeah? So here would be Landé factor and Bohr magneton. So let's first look at what happens in a zero magnetic field. This is the dispersion relation, so energy as a function of P. So we first forget this term and should be a vector. So it's a vector of Pauli matrices, it's a dot product. So, but this vector here will point in y direction, so it's only sigma y, and we will assume later that B is in the z direction. Yes. That's a vector product, that's a scalar product. So here we just have a P times sigma y term with some prefactor. So what does that tell us? Tells us spin would be conserved. We have either spin up in the y direction or spin down in the y direction. And then there's a shift either to the right or to the left of this dispersion relation. So p square over 2m plus or minus alpha p. So that looks like this. You have the parabola p square over 2m shifted to the right or to the left, depending on which spin you have. Yeah? For spin down, you get this curve. For spin up, you get this curve. So now in the next step, you switch on your magnetic field. So you have B dot sigma z. Sigma z doesn't commute with sigma y. So what will happen? This crossing here, it will become an avoided crossing. So there's a splitting, and you get an upper surface and a lower surface, where here it's approximately spin up, here it's approximately spin down. And the idea is now to put the chemical potential inside this gap. If you put the chemical potential, for instance, close to 0, you basically are removed from this upper branch, and the Fermi points only intersect here and here. While here we had 4 intersection points. And this is the trick to get rid of the spin, because now you see the right mover has basically spin up, the left mover has basically spin down, and that's a helical liquid or a helical state. So you got rid of the spin degree of freedom by enslaving it to the momentum. Yeah? Momentum tells you already what is the spin direction, and so one calls this a one-dimensional helical liquid. Spin of fermion is then enslaved by the momentum direction. In effect, you have gotten rid of the spin. Yeah? And the opposite momenta have approximately opposite spin, and now you include as the final step a coupling to an S-wave superconductor. And what that does is it basically looks like this. So one plots here the spectrum in a doubled way, because this BDG Hamiltonian is essentially having the electrons and the holes together. So you should then only take half of the spectrum to avoid overcounting. That's why here in the pictures it's dashed, and the second copy, it's always particle-hole symmetric. You can reflect at 0 energy and get the same spectrum. So this was the delta equal to 0 spectrum. Here we have our gap at 0 caused by the magnetic field. And then we just reflect the whole dispersion relation because of this BDG framework. Now let's switch on delta. Let's say for delta equal to 0.5b, what you see here is that at the Fermi points here, a gap opens. Yeah, you see here this gap opening. At the same time, this magnetic field induced gap starts to decrease. So it decreases here and eventually closes when delta is equal to b. And then as you increase delta beyond b, this gap opens again. That's the typical thing that happens when you have topological phase transitions. You have competing gap tendencies, namely a gap from the superconductor and a gap from the magnetic field, and they work in opposite directions. So first here you have only a gap caused by the magnetic field. You switch on the other gap causing agent, it will work against it, reduce this gap, eventually close it, and then here the gap from the superconductor wins, and you open a gap again. And it will turn out, we will see this, that for B larger than delta, so on that side here we have a topological phase, on that side we have a trivial phase. Yeah? Topologically trivial phase. So that means in this side here we will have Majorana bound states once we cut such a nanowire. Yeah? This we will now see in formulas, but that's really the picture behind. So this gap closing and reopening at 0 momentum will be the crucial thing that helps us to identify this transition. Yes, please. Yes. Then you have a non-local John-Wigner transformation, and yes, 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 exactly. Yeah. So now let's put these pictures into equations, and in that case, we again have a BDG Hamiltonian, but it's slightly more complicated in the sense that we have to use a 4-spinner. The upper two entries. So there's a bispinor that describes the particle sector, and the lower space, the time-reversed whole sector. And the conventions here, that you have here psi down dagger and minus psi up dagger, reflect the time reversal symmetry. Time reversal symmetry operator, or time reversal operator, is normally defined as minus I times the sigma y matrix in spin space times complex conjugation. Complex conjugation here means the dagger. And if you write down minus I sigma y, you have this matrix. So you really see, you take this one with the minus, you get it here, and dagger. So that's really the time reversed partner up there. And we need to really explicitly write down the spin because of the spin-orbit coupling. So that is not so easy as in S-wave. And so one has to avoid double counting, yeah? Because we have sort of artificially doubled the space to simplify life. But then we can, of course, make mistakes because we have artificially enlarged the space. Now, we use Pauli matrices sigma y here, sigma z, in spin space, and again tau in Nambu, particle hole space. And the Hamiltonian here, this BDG Hamiltonian in this language, has the following terms. First, we have, as before, the kinetic energy, p squared over 2m minus mu. And you see this couples to tau z, is spin independent. That's exactly as in the Kitaev chain. But now on top of that, we have the spin-orbit coupling. As I said, we take it here in the sigma y direction, and it's linear in our momentum p, and u is just proportional to the Rashba spin-orbit coupling. It's the constant that tells us how strong is this spin-orbit coupling. It couples to sigma y, and it's again a term that appears in the kinetic energy. So it couples to tau z. Now the Zeeman field is different. It doesn't have a tau z because this is a term that changes sign under time reversal. These don't, so they have to appear for the whole with the tau z. This doesn't, but it comes with the sigma z because the magnetic field here is assumed to be in the z direction. And finally, we have a proximity-induced pairing because it's an S-wave superconductor that does the pairing. There is a trivial structure here. It's just delta, no space derivatives or whatever. It acts in tau x because it couples, once we write down psi dagger psi, it gives you precisely psi dagger up, psi dagger down, or psi up, psi down. So it pairs two particles together. That's precisely what we need. Okay, so these are the ingredients. And now we do the same trick again with square. Yeah. Of course, I didn't write out the tensor products. You are right. Here there's a 1 in tau space, and here there's a 1 in sigma space. It's correct. So first of all, if we have no B field, no delta, we have the shifted parabolas. You see this directly here. Then we just have this kinetic energy, sigma y is conserved, and you have shifted parabolas as seen before. Now, if delta stays equal to 0, there will be a gap opening near p equal to 0. So if delta stays 0, we don't have that. We can focus, for instance, on the left upper branch by putting tau z to 1. And then you diagonalize this 2 by 2 matrix, and you find, indeed, this is the dispersion relation. You have avoided crossing at p equals 0. And now putting the chemical potential inside the gap, you will get a pair of almost helical states. So this psi p is just, didn't define it. The psi p is just p squared over 2m minus mu. Yeah, that's psi p. Okay, so now let's, for simplicity, take the limit that chemical potential is at 0, then it's really in the gap. And let's also assume that we don't have that we have a very strong spin-orbit coupling to simplify algebra. In that case, it's justified to drop again the p square term. Yeah? This I only need to drop the p square term and to simplify algebra. So mu is now taken to 0. We can drop p square term. We have only these 3 terms. And we will now look at the gap closing and reopening at 0 momentum, which is now described by this BDG Hamiltonian. Okay? So again, we do the squaring trick. So we get u square p square, we get b square, and we get delta square because all the Pauli matrices square to 1. Now we get cross terms. So first we have a cross term from this with this. But now you see sigma y times sigma z plus sigma z times sigma y is 0 because the Pauli matrices anti-commute. So there is no cross term from these two. And likewise, if you take this term, cross term with this, you see tau z anti-commutes with tau x, also no contribution. The only term that you can have is from this cross term with this. So b sigma z times tau x, it's just there, and you get the cross term minus 2b delta. So that's your squared Hamiltonian. And again, this is a conserved quantity, has eigenvalues plus or minus 1. And so this is just a shift in the Hamiltonian. And we can therefore see that the squared eigenenergies are given by e square p plus or minus. That plus or minus is precisely this eigenvalue. And then the rest is just a square b plus minus delta square. And the interesting point is again the minus sign. This gives you the lower energy, and you see that b minus delta square can vanish exactly at the phase transition when you have b equal to 0 and p equal to 0, the gap closes. Yeah? So that's exactly this vanishing of the gap at b equal to delta. And for b less than delta, we have a topologically trivial phase. For b larger than delta, one can check again. It's a topological phase that then has Majorana end states if you cut the chain in 2 halves. This was a discussion for 0 chemical potential. If you repeat the same with a finite chemical potential, the critical point moves to this value. And so in practice, you can tune such a wire into its topological regime either by changing the Zeeman field or by changing the chemical potential. The gap is usually not something you can change in a given experiment. Okay, so that's the idea. This was the proposal in 2010 by 2 different groups. Kitaev chain is basically realized using these semiconductor quantum wires with Zeeman field proximity coupled to S-wave superconductors. How can we see it in experiment? Of course, one possibility is the fractional Josephson effect. But as I told you, this is difficult because you have to make sure that the parity is conserved. And that in practice requires you to study dynamics. And then there are also subtle other effects. The thing that has been used so far in experiments is the zero bias anomaly in tunneling experiments. This I will explain now. And in the probably next lecture, we will turn to non-local effects in interacting devices. So once you add Coulomb interactions to the game, you get characteristic non-local effects that are predicted to give very characteristic features in transport experiments. So now I want to discuss this zero bias anomaly, short CBA. And the setup one considers is simply tunneling into the end of such a superconducting nanowire. And that can simply be done by having an overhanging part. So you imagine here's your nanowire, and here you bring in a close coupled superconducting electrode. So the superconducting electron stops here. It will proximity induce superconductivity in this part. Here we have basically a tunnel contact, and then the normal lead is just the overhanging part of your nanowire. Yeah, so you can then apply a voltage here and study the current voltage relation or the conductance for tunneling into this topological superconductor. And the modeling of that will be such that at low voltage, we can basically get into this superconductor only through this Majorana state. Because there is a gap You cannot reach these high energy quasi-particles if you come in with very low energy. And so the electrons, this is the spinor in this topological superconductor portion, will be projected down to this Majorana sector. And since we come from the left side, we just project it to the gamma 1 state, which has a wave function FL of x, and a spinor structure that you can work out looks like this. This will have this eigenvalue of the sigma z tau x matrix as we want it. We forget the other Majorana, assuming that this is a very long wire. So you cannot tunnel from here all the way over to there. And we neglect the quasi-particles above the gap. Yeah, that's the approximation one does here. So you tunnel into the Majorana state from a normal lead, and this gamma 1 in turn you can express as a spin-up superposition of electrons and holes, again with this wave function. Yeah? Similarly, the other Majorana fermion will have a spin down if you go through this algebra. So they have a spin structure encoded in these wave functions here. Okay, so that's the basic ingredients. So once you know how to express the electron operator on the superconducting side, you can just use the standard tunnel Hamiltonian that transfers an electron from the left to the right, inserting this expression that we just had for the electron operator on the right-hand side. You will get something like this. So you tunnel by tunneling out an electron with spin up in y direction into this Majorana state, or vice versa. You go back from the Majorana state and create a particle in the wire, and the sum over k basically means it's a local process. So you look at the electron operator at the position of the contact. So these Vk are tunnel amplitudes that describe you how these are connected. So using a tunnel Hamiltonian, one can derive, and I will come to that in the next lecture also, you can derive that one should see a conductance peak that at 0 temperature goes all the way up to 2e squared over h. At finite voltage, it will be broadened as a Lorentz peak with a width given by the hybridization, so essentially the squares of these tunnel matrix elements. That's this gamma that gives you basically the line width of this Majorana fermion because it can escape to the leads. Yeah? So that's the usual line width parameter that sets the width of this Lorentzian curve. The interesting point is that the peak height at 0 temperature is 2e squared over h. And that sounds a bit strange first because we have now spinless electrons effectively. Only the spin up in y direction plays a role here. That's the only one that couples to this Majorana fermion. And usually the conductance per channel is e squared over h. But the resolution is, of course, this is Andreev reflection. So what happens is on this side here, you come in with an electron with spin up in y direction, and this will be reflected as a hole. That's Andreev reflection, thereby transferring a Cooper pair into this topological superconductor. So you transfer two charges in such a tunneling process. Yeah? That's Andreev reflection, and because of this 2e being transferred in a step, you get conductance 2e squared over h in Andreev reflection. And that's a conductance peak or zero bias anomaly in the sense that there is a definite peak in here. Now let me briefly come to the experimental signatures of this type of physics. So as I said, we expect in indium arsenide or indium antimonide nanowires to see Majoranas with the interplay of strong Rashba spin orbit, coupling, magnetic Zeeman field, and proximity-induced pairing. So these are materials that have a strong intrinsic spin orbit coupling, and when the magnetic field is tuned to sufficiently big values above this gap scale, which is typically of order 1 millielectron volt or 0.5 millielectron volt, say, then you can hope to see these Majorana fermions, at least in sufficiently clean materials. Yeah? And they can make these nanowires with mean free paths of a micron in the meantime. So the setup that I'm showing here is probably the most famous one, and probably most of you have seen these pictures before. This was the experiment in Couwenhoven's group in Delft, which was the first and very widely announced report of Majorana fermions. So what they did is they had here an indium antimonide nanowire. Here you can see it on the AFM picture. Here there is a superconducting, I think it was niobium electrode, that proximity induces superconductivity in this part of the nanowire. This overhanging part here serves as a normal electrode, and then it's coupled to some bulk metallic electrode. So here's the cartoon again. So you come from a normal superconductor. There is a finger gate here that allows you to tune this tunnel contact to the topological superconductor wire. And presumably here there is a Majorana fermion. Yeah? So once we are in this topological phase. And the way to look for it is then to measure the conductance. Notice that this superconductor is grounded, so you study the current flowing from the normal lead and then suck it off from the superconductor. Yeah? And what we expect is a zero bias conductance peak due to resonant and wave reflection. So what they see in the experiment is indeed here, so there are different conductance traces versus voltage, and one sees indeed a peak emerging for sufficiently big magnetic field, and it sticks to zero. Yeah? It sticks to zero regardless of what kind of parameters you have. The height is not 2e²/h, but around a factor 10 smaller, but that's because they're at finite temperature. So the temperature is above this hybridization scale delta, and then you expect a reduction factor roughly given by gamma over T. Yeah, and so that seems to be okay. They also checked in these pictures what happens when you change the magnetic field so that you really have such transitions. It all seems pretty reasonable. However, there have immediately been some reports that you could also explain these data by alternative mechanisms, at least parts of these data. This order, for instance, can induce such peaks. If you have smooth confinement, it can mimic these data, or you could possibly have Kondo physics in the game that also causes such peaks. There are now much nicer data by Charlie Marcus' group, not yet publicly available, but I think the consensus in the community is more and more coming to the conclusion that indeed probably also in these experiments they already saw the Majorana bound states. In any case, what we will do in the next lecture is, as theorists, we can just assume, let's say they have it, and see what interesting things we can play with these Majorana fermions. So the conclusions of this second part are as follows. I have explained the bulk boundary correspondence in the example of the Kitaev chain. Yeah, so in a bulk topological phase, we can define these topological invariants. This bulk topological phase has a sensitivity to boundary conditions. And once we are in a non-trivial phase, cutting it means we have edge states. For the Kitaev chain, these edge states are just the Majorana bound states. Zero energy modes. Yeah? The main part of today's lecture was to show you that we can realize this Kitaev chain in semiconductor nanowires. The interplay of spin-orbit coupling with sufficiently strong Zeeman fields and proximity-induced superconductivity can then mimic the physics of the Kitaev toy model. So you can really study this in the lab. And that's getting a very exciting field now, because if they can really reliably produce these Majorana fermions, we can play games like braiding, non-abelian anyons, and so on. And I think that will still be a lively topic for future research in the next decade or so. So in the next lecture, I will not start now, we will switch from the so far non-interacting problem and study correlation effects that will couple the Majorana and the Cooper pair dynamics when we have devices that are not grounded but floating. So far these experiments were done in grounded devices. If the device is floating and you have to require current conservation, then we will see that we can get novel non-local effects, eventually culminating in the topological Kondo effect. We will start with the simpler case of a single charge transistor tomorrow, and then continue with the topological Kondo effect. But I think I stop at that point. Time for lunch. Yeah. Well, it's like it's a question of belief to some extent. Of course, you cannot rule out that one of the alternative mechanisms was responsible for that in these experiments. So one has to see the full picture of all the experiments that have been done. As I showed you on that slide, there are many other papers that in the meantime have seen similar features. For instance, there has been a very nice experiment using a different realization, namely magnetic atoms deposited on a conducting surface. And then there is a self-sustained state that can support Majorana fermions. However, I think these magnetic realizations will not be so useful for devices later on. I mean, the nice thing with these semiconductors is that there's a lot of technology available, and I mean, they can put it on wafers and directly do networks out of this and hope to do some real progress soon. This will not be possible with these STM structures, which are delicate objects. So I think the majority of people in the community will say, yes, we think this is already the Majorana, but there are people, I can give you names if you want, that say, no, it's not yet there. That's the situation. Yeah. I don't understand where would you put the here? Oh, see here, yeah. Yes. Yeah, that's what I will do in the next lecture. So we will do a transistor basically. Yeah. We have two Majorana bound states and normal leads. This I will discuss next. Yeah, this I will discuss in the next lecture. Yeah. You mean for applications, for instance? I mean, we are currently working with Stefan on a surface code built from Majorana networks that use such things. That could be much, much simpler than the schemes that Volodya was talking about, for instance, based on Josephson junction, where you need zillions of ancilla qubits and so on. So the hope could possibly, of course, these braidings, I mean, that's really the thing that drives you in this field, the hope that you can eventually do quantum computation with it. That's the major driving force. Whether this will come out in the end, I don't know, but I think it's interesting physics in any case. Yeah.